Good evening, everyone. Welcome to the seventh problem solving session for the course Environmental Remediation of Contaminated Site. The course instructor is Professor Bhanu Prakash Velanki from IIT Roorkee, and I am one of the TA for this course. I am a PhD scholar from IIT Kanpur. We will start by going like previous week. We will go to the briefly towards the lectures, which was five lectures which were there in week 7, and then we will try to solve previous year questions based on the material for week 7. So before that, this course, that is environmental remediation of contaminated sites. So the course started with introduction about the hazardous management rule in India, which is hazardous management transboundary and movement rules 2016. And then in the week 1, we have seen the other management waste management rules like biomedical waste management. Then we have seen rules for municipal solid waste management and others. And then we have also discussed about what are the risks from the carcinogenic and non-carcinogenic compounds. So we have done the risk characterization. So in risk characterization, so for carcinogenic compounds, we take the entire exposure ill effect for the entire lifespan of the individual, and for hazard and for non-carcinogenic compounds, we find out the hazard quotient based on the exposure time and duration. And then we move to week second. So in I think sorry, in week 1 also there was a detailed description about the hazardous waste management rules, in which we have seen a very important characters method for characterization of hazardous waste, that is TCLP test. So this is the toxicity characteristic leaching procedure test. So on the basis of TCLP test, we classify a waste as hazardous or non-hazardous. Suppose if a waste is within the limits given by have for different pollutants. If the waste, if the limits in the waste is below all those limits, then the waste will be considered non-hazardous, and then it can be sent to the municipal landfill for disposal. But if the waste fails the TCLP test, then the waste is sent to hazardous waste landfill. So that's why in TCLP test, what is first is done based on the basis of whether the waste is a solid or liquid. There is different procedure for preparation of the sample, and if the waste is solid, suppose, then there is, so first of all, there is particle reduction to less than 9 mm, and then on the basis of the pH of the sample, whether the after addition of HCl pH is checked. If the pH is below 5, then we use a different extractant solution, and if the pH drop is above, not below 5, it is above 5, then we use a different extractant solution. So the pH of these extractant solutions are different. And then the solid to liquid ratio, or the waste to extractant ratio, is taken as 1 is to 20. And then waste and extractant solution are added, and then they are shaked on end to end shaker for 16 to 20 minutes. And then we find out the concentration of different pollutants in the extractant. So this was the test for TCLP test. I think TCLP test is again there in week 8. So we will see detail about TCLP test there. And then in next week, week second, we have seen risk characterization and hazard index identification for carcinogenic and non-carcinogenic compounds. And then the method for remediation of contaminated sites started. So the first method was pump and treat method. So the first method was pump and treat. So suppose if there is some pollutant in the aqueous phase, then we can pump the entire groundwater, treat at the on the surface, or and then we can either use that treated water for other purposes, or we can again recharge the groundwater with that treated water. So in pump and treat, we have seen that if the pollutant is a fraction between or adsorbed on soil and sediments, and it is also in the aqueous phase, then the time for treatment according to pump and treat is very high, and we have find out the retardation factor for that. And again, we have seen if there is non-aqueous phase liquid, then also the retardation factor multiplies in respect to when there is sorption. So for pollutants and for aquifers where there is non-aqueous phase liquid, so pump and treat method is not ideal for these cases. So we have solved numericals based on pump and treat method where we have find out retardation factor, and then we move to the next method which was permeable reactive barrier. So permeable reactive barrier, as the name says, there is a permeable layer which allows the water to flow through it, but the pollutants are trapped based on different mechanism. Either it can be sorbed or it can be precipitated and so on. Also, also there can be redox reaction where the pollutant is either getting oxidized or reduced to a lesser uh, uh, toxic form. So in permeable reactive barriers, we have seen I think a case study from a site in Utah in US where there was the site was remediated using permeable reactive barriers. So in permeable reactive barriers, we have solved numericals based on the design of the reactive barriers where we have tried to find out the thickness of the reactive barriers, and also we have find out how much mass of the uh, I think zero valent ion that was required for treating that pollutant. And then we move to the next method. I think that is natural attenuation. So in natural attenuation, we have seen that microbes, they have microbes can take the pollutant and they can convert it into some other form which can be non-toxic. So in natural attenuation, we can see that it can be remediation can be of two types, destructive and non-destructive. So in non-destructive, the phase of the compound does not change, but in destructive, the compound is converted from one form or one to other. So in natural attenuation, we have seen that we can remediate the sites by adding different microbes, engineered microbes, or we can modify the operating parameters in the aquifer that will be favorable for remediation of the pollutant by microbes. So in natural attenuation, we have solved a few. I think last week we have solved two numericals using the Excel sheet where we were trying to find out the rate constant for the degradation of the compound. And then, so we have solved two numericals based on one of the numerical consider only sorption, and the second one which considers sorption along with advection, which is the real life scenario. So we solved few numericals based on that, and then in week 7 is continuation of natural attenuation here also. So here we will see, I think there will be a case study, and then uh, we will see a case study based on Muradabad in India, and then we will uh, move to the next method, that is the solidification, stabilization, and solidification. So let me share my screen and directly go to the lecture slides. So first lecture is of the result of the case study which was there in week 6. So there was a site contaminated with TC. So and there was a river nearby, and there was different types of soil sediments present in the aquifer, and so this table shows the screening parameters and scoring. So based on different parameters, scoring was done. So suppose for dissolved oxygen concentration for natural attenuation, the concentration should be 0.5. And here we can see that in shallow aquifers, the concentration was 0. So a score was given for that. And in deeper aquifers, the concentration was high. It was 0.92. So 0 score was given. So for different parameters, different based on the uh, fulfilling criteria, different scores was given, and we have seen in week 6 that the concentration of other or other reducing or electron acceptor compounds was very less, and because we have seen that the concentration of nitrate, sulfate, iron, or dissolved oxygen, all these were very less. So the pollutant which there was present, that can act as an electron acceptor. So here we can see that oxygen and nitrate is oxidizing agent or electron acceptor and have more electronegativity than chlorinated compounds. So their concentration should be less. So which I was telling that if there is some chlorinated compounds which need to be act as a electron acceptor, then the other electron acceptors which have higher affinity for taking electrons should not be there present. Otherwise, those high electron affinity compounds will act as the oxidizing agent, and the chlorinated compound will remain as so. And here in the system, iron and sulfide will act as electron donors, so their concentration should be high. And here we can see that concentration of iron is high. So in the deeper shallow aquifers, it is quite high. So based on that, score was given. Although the concentration of sulfide is very less in the aquifer, but we have one of the electron donors, that is iron. So based on different all these criteria, different scores were given. So based on that, a six-step screening method was done for remediation. So this is the screening method. Please go through these in the lecture video. So then estimation of contaminant transport velocity was done. It was done by finding the hydraulic gradient, conductivity, and porosity. So this table shows the head in different months, and the hydraulic head was fine, and it was seen that it was different throughout the year. And then the variation in the groundwater level throughout the year was found out, and that vertical transport velocity was calculated, and based on all these, retardation or biodegradation rate parameters were determined. So we know that partitioning coefficient is KOWN to FOC. So based on all the experiments or data present, so this partition coefficient was developed for that particular contaminated site. And then the retardation coefficient or retardation factor was found out for different contaminants. And then the first order rate coefficients were found out, and these calculations were done. And the concentration of different pollutants we were having, and it was seen that there were some byproducts formed by degradation of the polluted. So it was seen that natural attenuation was taking place in the aquifer. So based on these, this site was remediated based on natural attenuation, and then the next lecture was about soil and sediments contamination. So here a site about Morada case study for Moradabad is done. So a typical landfill will look like this. So it will have a impermeable layer. So for hazardous waste, so there are two impermeable layers, but for municipal solid waste, there is only one impermeable layer. So there will be an impermeable layer or geomembrane which blocks the flow of leachate from this landfill to the below groundwater, and there will be a clay layer above that, and then there will be a perforated pipes that will be in the sand. So these perforated pipes will collect the leachate, and that leachate will go for treatment, and again this layer will be repeated above that, and above that the waste will be deposited in different cells and covered with soil every day. So here is a image of the landfill. So these black covered are the cells. So for each day, a waste is dumped in a particular size, and that is known as cell. And at the end of the day, those cells are covered so that they are not open to animals or other organisms can come in contact with that. So then we have lecture 33. This is the case study of Moradabad. So there is a video also in this. So please go through this in the lecture slides. Now let's go to lecture 34. So there was a open source document which was discussed, that is on the assessment of performance of engineered waste contaminant barriers. So let's come directly to the stability failures. So here we can see it is a rotation sidewall slope and base failure where the slope has failed. It is a rotation type failure where the material from here has come at the bottom and it has accumulated at the end of the slope. Next type of failure is the uh, pull out of a liner system components from anchor trenches. So here is the anchor trench, and this material will come and this will come at the side of the slope. So next type of failure is failure through the waste pile. So waste pile, they can slightly slope. They are making each day at the in a cell, so they can slightly slope away from that particular cell. So here it is a foundation. Here it is a so here it was a failure in the foundation, waste liner, and next is the failure by sliding along the landfill liner system. So we will see few numericals based on these failures also. So next we will try to find out the flux due to diffusion and advection. So uh, overall formula for these flux were derived in the next lecture. So we will try to solve two numericals based on these also. Next, solidification and stabilization is has been started. So solidification is like it is a process that binds a contaminated media with a reagent, changing its physical properties. So solidification and stabilization it is a technology to prevent the further migration and exposure of the contaminants from the contaminated media. So in this, either solidification is done where a reagent is added so that it can bind the pollutants in the soil and confine the mobility of the pollutants. And next is stabilization where something is added which involves a chemical reaction and that reduces the leachability of the toxics, leachability of a waste. So the factors which need to be considered in the selection of stabilization and solidification is treatability studies and solidification and stabilization specification to evaluate performance. So the type of contaminants to be treated, cost consideration and long-term performance. So the reagents we are using to bind or reduce the leachability of the contaminant that should last for a long period of time so that the pollutant is not getting more mobile. So the difference here for solidification and stabilization is given that solidification is a process that binds a contaminated media with reagent, changing its physical property by increasing the comprehensive strength, by decreasing its permeability or encapsulating the contaminants to form a material. So in solidification, we add some reagent which can uh, decrease the permeability. So if the permeability will be decreased and if water will be passed, then again the water will not be able to flow that freely as compared to highly permeable media, and so the pollutant release in the water will be less. And if we will make the some solid bricks or something like that of that soil, then again the pollutant will not be able to uh, come out from that. Next is stabilization. So it involves a chemical reaction which reduces the leachability of the waste and it chemically immobilizes the waste. So suppose a soil is polluted with a pollutant, and we what we want to do is that do not want to remove that soil and treat it. So what we want is that we want to confine the contaminants in that particular soil. So we can add some stabilizing agent which will reduce the leachability of the pollutants in that soil. So the groundwater and the surface water will not be polluted, because if the water will flow, the leachability of the pollutants has been reduced. So the pollutants will not come into the aqueous phase, and like that, the site can be stabilized for preventing the spread of the pollutant from that soil to the surrounding environment. So I think these were the lectures. So we have seen two case studies here, and then we have seen different types of flux for advection and diffusion, and then we have seen this basic concept for solidification and stabilization. So now let's go and try to solve the questions. I think. Okay, let's go to the first question. So the question is, so first and second question are two numericals, so we'll try to solve the numericals at the end. So the first question is, the various steps required for monitored natural attenuation are given below. So the first step is analyze site data to determine if biodegradation is occurring or not. B is estimate biodegradation rate constant. C is determine groundwater flow and solute transport parameters along core of plume. D is compare the rate of transport to rate of attenuation using analytical models. E is locate source and potential point of exposure. And F is after all screening criteria are met, proceed with detailed feasibility analysis. So we have to select the correct sequence in which these steps are done. So I'll give you all 4 minutes. Just take your time and write the option which you think is correct in the chat box, and then we will discuss. So the C is correct option, D is not the correct option. So the first step is analyze the site data to determine if biodegradation is occurring or not. And then we locate sources and potential point of exposure. And then the next step is determination of groundwater flow and solute transport parameters along core of plume. And then the next step is estimate biodegradation rate constant, followed by compare the rate of transport to rate of attenuation using analytical models. And finally, the last step is after all screening criteria are met, proceed with detailed feasibility analysis. So the various steps for monitor natural attenuation follows the order as given in option C. So now let's move to the next question. So the question is, please select the correct name of the type of failure shown below which can occur at a hazardous waste landfill. So the first option is base failure. Next is failure due to the waste pile. C is failure by sliding along the landfill liner system. Or D, failure through the waste liner and foundation. So this figure is given and we have to find out what type of failure it shows in a hazardous waste landfill. So again, I will give you all 4 minutes. Just take your time and write the option in the chat box and then we will discuss. Got one answer is A, base failure. So this is not base failure. So here we can see that the base liner has failed. It has slanted, and the waste, this is the waste fill, which is also this it has failed through this line. So waste fill has also failed, and also we can see that the foundation is soft. So because of the soft foundation, this failure has occurred. So the here failure is the failure through the waste, liner and foundation. These three have failed because the foundation is soft, the liner has inclined, and also the waste slope has failed. So the type of failure here is D, that it shows the failure through waste, liner and foundation. So now let's move to the next question. Sorry, the question is, so the remediation of a TCE contaminated site involves microbial attenuation where microbes break down TCE into simpler compounds like 1,1-DCE, VC, chloroethane and ethane. A change in surrounding conditions causes a decrease in system temperature. What impact will this temperature decrease have on the degradation process? So here a case is given where microbial attenuation is taking place, and because of the surrounding condition there is a dip in system pH, and we have to find out what will be the impact of this temperature decrease on the degradation process. So the first option is the rate of degradation will increase and the mentioned simpler compounds will form. Option B is the rate of degradation will decrease and the formation of simpler compounds may not occur to the extent they would if the temperature did not decrease. Option C is the rate of degradation remains unaffected, or D, none of these. So again, I will give you all 4 minutes. Just take your time, write the option in the chat box, and then we will discuss. So let's see which is the correct answer. So the temperature in the system is decreasing. So with decrease in temperature, the rate of degradation will decrease because these the microbial degradation generally takes place in the mesophilic temperature, and a general trend is seen that with increase in temperature, the activity of the microbes increases, but this increase is still to a particular temperature, a particular optimum temperature. After that, further increase in temperature will leads to killing of the microbes, and the degradation rate decreases after that. And also, if there is decrease in the temperature, then with decreasing temperature, the microbial activity decreases. So because of that, the rate of degradation will decrease. And because the rate of degradation has decreased, we have seen in the question that with the microbial attenuation, simpler compounds like 1,1-DCE and VCE are formed. So since the rate of degradation has decreased, the formation of the simpler compounds may not occur to the extent they would if the temperature did not decrease. So B is the correct answer. That with decrease in temperature, the rate of degradation will decrease and the simpler compounds will not form that much that would have formed if the temperature would not have dropped. So B is the correct answer. So now let's move to the next question. So the question is, which of the following tests is not used to identify the hazardous nature of a waste? So the first is toxicity characteristic leaching procedure, that is the TCLP test. Option B is soluble threshold limit concentration. C is the waste extraction test, or D pH test, or this pH shows the corrosivity, or E none. So we have to find out of all the four tests given, which is not used to identify the hazardous nature of a waste. E is the correct answer. That toxicity characteristic leaching procedure, TCLP test, then soluble threshold limit concentration. So this test is also done for hazardous waste. And the waste extraction test involves various tests for the hazardous waste. And next is the pH test. So it tells about corrosivity. If the pH will be very high, more than 12, or if the pH will be very less, 1 or less than 1 or 2. So then it tells that the compound is very corrosive in nature. So pH test also test about the hazardous nature of a waste. So D is the correct answer, that none of the given method. So all of the given method are used for the hazardous nature of a, to identify the hazardous nature of a waste. So E is the correct answer. So let's move to question number 7. So the question is, a proposed hazardous waste landfill in a state includes factor like an impermeable layer, HDPE liner, leachate collection system, and leak detection system in its design. However, the design does not include a gas vent. Choose the appropriate reason for not incorporating a gas vent in the hazardous waste landfill design. So the first, so in municipal solid waste landfill, there are gas vents for the for the collection or for the collection of the methane, CO2, and other gases which are formed during the anaerobic degradation. So these there are proper gas collection systems. So these gases are collected, or they and then they are used for different purposes, or the methane is flared and converted to CO2. But in the hazardous waste landfill design, there is no gas vent pipe. So we have to find out why is so. So the first option is the hazardous waste being highly compacted prevents the upward movement of produced gas, trapping it within the landfill. Option B is the gas produced in the landfill undergoes reaction with the compounds, converting it into simpler products. Option C is the hazardous waste landfill has low concentration of organics and reduced microbial activity, leading to minimal microbial degradation and the formation of gases as a product. Or D, none of the above. So, four options are given. We have to select which of the following is correct. So, again, I will give you all 4 minutes. Just take your time, write the option in the chat box, and then we will discuss. So I got one answer as C. So C is the correct answer. That the hazardous waste has a very lesser organic concentration. So that's why since the organic concentration is come, so organic carbon will not be present for the microbes to degrade the waste. So that's why very less microbial degradation is seen, and that's why the formation of gases as byproduct is very less. On the other hand, municipal landfill have very high amount of organics present because of the food waste and also because of other types of waste like tree cuttings and all. Sorry, if the food waste and the tree cuttings and other if they are not sorted, they go into the municipal landfill. Then they have very high concentration of organics, and these organic carbon these organics are carbon which serve as a source of food for the microbes, and microbes fed on them, and because of absence of oxygen into the landfill, anaerobic degradation takes place, and methane, CO2, and other gases are formed. So, but in the hazardous waste landfill, the hazardous waste have very less amount of organics. That's why the microbial degradation is very less. So, these type of gases, these gases will not be formed. So, there are no vents for collection of the gases. So, C is the correct answer. So, now let's move to the next question. So, the question is the factors affecting treatment selection in solidification and stabilization are type of the contaminants, cost, and long-term sustainability of the treatment. We have to select whether this statement is correct or not. So again, I'll give you 4 minutes. Just take your time, write the option in the chat box, and then we will discuss. So let's see which is the correct option. So the statement given is correct, that the factors which affect the treatment selection and solidification and stabilization are the type of contaminant, cost involved, and the long-term sustainability of the treatment. So A is the correct option. So let's move to the next question. So the question is, the rate limiting step in a chemical reaction can be defined as the step that liberates the most amount of energy in the overall reaction. So again, we have to state whether the given statement is correct or not. Again, I will give you all 4 minutes. Just take your time. Write the option in the chat box and then we will discuss. So the statement given is false. So the rate limiting step will be the slowest reaction step in the overall reaction. So since it will be slowest, so the energy liberated will be the least. So that's why this statement is wrong, that the rate limiting step in a chemical reaction can be defined as a step that liberates the least amount of energy in the overall reaction. But here most is given, so B is the correct answer, that this statement is wrong. Now let's move to the next question. So the question is concerning leak detection systems. Consider the following statements. A. The presence of leachate in leak detection system serve as an alert for the improper functioning on the primary leachate collection system. B. The leak detection system only contains an HDPE liner to prevent leachate from contaminating the subsurface. So we have to say whether A statement is correct or B statement is correct. So there are four options given. So we have to select the correct option. So please write the correct option in the chat box and then we will discuss. So let's see which of the given statement are correct. So the first statement that the presence of leachate in a detection system serves as an alert for the improper functioning of the primary leachate collection system. So this is correct. And the second option that the leak detection system only contains an HDPE liner to prevent leachate for contaminating the subsurface. So this is not correct. So there are HDPE liner, a clay layer, and impermeable layer is also there. Impermeable zero membrane layer is there. So B is not the correct answer. So B is incorrect answer statement. So option A is the correct answer. That A is correct and B is incorrect. So now let's move to the next question and try to solve two numericals. So the statement is at a remediation site, the groundwater contaminated with trichloroethylene is flowing towards a river. Tortuosity factor is given, diffusivity is given, porosity is given, hydraulic conductivity and hydraulic gradient is given. And the question is if the concentration gradient at a specific plane within the system is 320 milligrams per liter per meter, then the diffusion driven flux is, so we have to find out the flux due to diffusion. So I'll give you all 5 minutes. Just take your time. Try to solve this question and write the value which you are getting. Okay, so the hint for the, let me write the formula for diffusion driven flux. So the flux due to diffusion is given as porosity times diffusion coefficient into dc by dx. So we have been given porosity. We will have to find out the diffusion coefficient, and the concentration gradient dc by dx is also given. So the diffusion coefficient is find out by using the formula, that is diffusibility divided by the tortuosity factor. So dE will be given by diffusive diffusivity divided by tortuosity factor. So this is the formula to find out that the diffusion coefficient. So we just have to put the values and we can get the diffusion driven flux. So I will give you all 5 minutes to do the calculation, and everybody please write the value which you are getting in the chat box. Okay, let's see what flux we are getting. So we will first find out the diffusion coefficient. We have been given the diffusivity, that is 9.8 into 10 raised per minus 8 meter square per second, divided by torsosity factor is 1.95. So we are getting 5.026 into 10 raised per minus 8 meter square per second. Now we will know the porosity, we know, and in the question, the concentration gradient is given. So concentration gradient is given, it means dC by dx is given. We can also see from the unit of this concentration gradient, it is concentration, that is milligram per liter per meter. So dC by dx. So the flux diffusion driven flux will be, we have porosity as 0.33 into the coefficient we have find out as 5.026 into 10 raised to the power minus 8 meter square per second. Okay, we have to multiply with the concentration gradient, that is dC by dx. It is given as 320 milligram per liter per meter. So we will convert the liter into meter cube. So to convert liter into meter cube, we need to divide by 10 raised to the power minus 3. So this will be the milligram. To convert liter into meter cube, so 10 raised per minus 3. So meter cubes into meter will be the meter raised to the power of 4. Now we have to find out the diffusion driven flux in microgram per meter square per second. So to convert it into milligrams into microgram, so we will multiply by 1000. Now let's see what value we are getting. So after doing all the calculation, we will get the final value as 5.307 microgram per meter square second. So this is the diffusion driven flux. So I hope this question is clear to you all. Now let's move to the second part. So the question is, if the concentration of Tc is 130 milligram per liter, then the advection driven flux is given by. So the flux due to advection, it is given by KIC. So K is the hydraulic conductivity, I is the hydraulic gradient, and C is the concentration. So from the previous question, hydraulic conductivity is given as 1.3 into 10 raised power minus 6 meter per second. We have the gradient as 6 centimeter per meter, and we have been given the concentration of Tc. So I'll give you all 2 minutes, just do the calculation and write the value for the flux in the chat box.